不行吗？这个
I'm glad they tested it.
可以，好，可以，好，时间已经是3点半了，是吧？4点半，我说错了。静音，那么今天是
No, you can't do like that.
Don Zagier 的
That doesn't work. It won't work. You have to switch.
He studied with Professor Gersbrook as PhD, and he wrote his dissertation on characteristic classes, and he got his PhD when he was 20. And at 24, he was named full professor at the University of Bonn.
That's not
24 only.
For 1 week, yeah.
Professor Zagier is a pure mathematician of broad interest. He works in nearly 20 subfields of mathematics and physics. In fact, he published 170 papers already with more than 100 collaborators. He has made many, many great mathematical contributions. For example, a gross Zagier formula is a great result with deep application to BSD conjecture. I think many of you probably don't know BSD conjecture. This is a $1 million program.
Next Thursday.
Professor, many prizes. Let me name of only a few. The AMS Core Prize, that's in 1987 or something. And also this month, the Fudan Zhongzhi Prize. This is $3 million Chinese yuan.
Yeah, Chinese yuan. Yeah. Kind of dollars.
And also he was elected to the American National Academy of Sciences in 2017. Today, we are very happy to have a great and a right mathematician to tell us how to ask right problems in mathematics. Please.
Sure. So first, thank you, Professor Zhang. Thank you, Jiping, for this beautiful introduction. It's one of the nicest I've ever had. It's really, I appreciate it. such a nice story. I should apologize for various things. One is my nose is a little stuffed, so if you don't hear me well, I will try to talk loud. There's no echo. I hope everything works. Secondly, I was told that this lecture is for people of all different faculties. Although when I look around, most of you look like mathematicians, I think. Just out of curiosity, who is not a mathematician? Please raise your hand. Oh, relatively few. Anyway, but perhaps in other universities. So I will try to avoid formulas. I will not assume you're mathematically trained, but I hope it will be interesting anyway. The other thing that I want to say, of course, is that I'm incredibly happy to be here in SUSTech and in China. Again, it's been several years. I have actually an agreement with the university to come every year for 1 month, but last year, you can imagine the reasons, was impossible. This year, 1 month would have been equally impossible because 3 weeks of quarantine out of 1 week, 1 month. So I came for 2 months. I hope by next year I can come and each year. So I hope to have a long and fruitful collaboration. Well, I don't know about long, I'm 70, but anyway, fruitful collaboration with SUSTech, and I'm really happy to be here. So I should start. By the way, can you hear me? So 2 things. If you can't hear, if it's not clear, or if I speak too fast, my English is sometimes, even for native speakers, very fast. Or if I say something you don't understand, please raise your hand and ask. Don't be shy. You can raise your neighbor's hand so they think it's your neighbor. But I want feedback if it's at all possible. So, as I said, my theme today is, well, the title is What Makes a Good Mathematical Problem? That's a kind of an odd title. And what I wanted to explain with that is that, in my view at least, mathematics is not like the other sciences. So if you're a medical researcher, you cannot choose, I want to study this illness. It's very, very rare, but it's very interesting theoretically. People want to study cancer and COVID and diseases that kill people. You have kind of a duty, if you're a good researcher, to study the important questions. You can't choose a problem just because it's interesting. Similarly, if you're an engineer, you might want to build a bridge from one skyscraper to another because it's a wonderful technical problem. How do you do this? But nobody wants that bridge. You have to build the bridge that they need. And even if you're a more basic science person, like say a physicist or a chemist, of course that is more fundamental, so you can do much more theoretical things, but still there are certain compounds, certain chemical process, certain physical process that we really, really want to understand, interactions between elementary particles, and those are the ones you want to study. You cannot pick something extremely rare and specialized just because it's a nice theory. But in mathematics, it's different. In mathematics, you choose the problem. Now, you might think this is like very selfish. I should study the problems that are important. But the experience of, I would say, hundreds of years says that nobody knows which problems are important beforehand. Of course, there are applied mathematics problems that come up that we have to solve and people work on them. That's clear. I'm not saying that applied mathematics isn't important or doesn't exist. But pure mathematics that is based on the idea, if I do this, there will be that application, will never work. Because the really good applications are usually completely unexpected, often many years later, often after the originator of the idea has died. You cannot work in a short scale. So for the really great discoveries, you have to think on kind of a big scale. So I've several examples. One is, maybe I use the board if I can remember how the chalk works. So for instance, already in the 17th century, binary numbers were invented, actually much before, but let's not go into historical controversy. And in the 18th century, also it's not quite true, but let's pretend, Boolean algebra. No, sorry, this is certainly wrong. That maybe is also wrong, 18th. I'm thinking Italian style, you subtract 1. Boolean algebra, it's called. I'm not assuming you know what these fields are. Actually, I don't know anything about Boolean algebra, but this is completely necessary to invent computers. You cannot do computers without them. But this was invented in the 19th century and in the 18th century. If people had thought, how can I make something to make a computer? They would have had to wait till 1960. And then it wouldn't have happened. And we would still be using computers now like people did 50 years ago. It's because these things were there that it could work so quickly. So another example, my field of mathematics, number theory, well, number theory is a big field, but let's say prime numbers. If you don't like that thing, this sign doesn't mean something on your phone, it means a number. And factorization, this is really completely pure and completely abstract, and it obviously cannot have any application, but it's got an extremely important application. You all use it every day when you pay with WeChat or anything like that. This is security, so cryptography, encoding, computer security. We couldn't have modern life without it. So even things like paying your bill in the restaurant, somebody in the background is using factorization of large numbers. Another example, which I like less because I don't really know the field, there's a rather strange field of mathematics that was popular about 30 years ago, 40 years ago, I remember, and then it kind of went out of fashion. It was called fuzzy logic, which was kind of a joke because fuzzy logic is a rude way in English to say that the person you're talking to does not think clearly. But fuzzy logic was a connection between logic, which is very precise, and statistics where things can be mixed. So something is not true or false, but 30% true, 70%. This was completely theoretical and looked actually crazy, but that led to improving. I won't write it all out, but for instance, if you go on a high-speed train or you use even a washing machine, they used, if the washing machine was on very strong, it used to move all around the room. Now it's completely stable. And the high-speed train, it completely absorbs every bump. And that's because the computer is interpreting the input with fuzzy logic. If you try to compute exactly, the train will keep budging. It's very surprising. And then my personal favorite is that an algorithm called LLL. This is Lenstra, his brother, and Lovash. They're all three friends of mine. One is a very good friend. They invented an algorithm 30 years ago in my field, in number theory. And that algorithm is for a problem that sounds extremely abstract. How do you find a short vector or the shortest vector in a high-dimensional lattice? So a lattice is something like this. This would be a two-dimensional lattice, and then a three-dimensional lattice, it would go this way. I can't draw it. But you can imagine a 30-dimensional lattice, but of course you can't picture it. But with their algorithm, you can find a short vector quickly on a computer in a 30-dimensional lattice. That had a huge application that you all use every day if you drive or if you take a taxi. GPS would not work without that. It existed before, but it got you within half a kilometer of your destination. Now it brings you to the door. And that improvement comes from using something from number theory. So just to say that pure mathematics does, of course, have applications, but all of these were much, much after the people who invented the thing made it. In this case, only 30 years, but it was certainly not invented for that purpose, and never would have been, because nobody would have realized that was the application you needed. So, but the point I want to make is not just that. So we have to choose. So that's what I started by saying. A mathematician is allowed. So I was saying other scientists do not have the freedom always to choose any subject because they have to choose something that's useful for the world in some sense. But I say that a mathematician not only can, but he must, he or she. If I say he, it does not have any implications about the gender of mathematicians, and must choose by individual criterion that you cannot quantify. So personal taste, beauty, aesthetics. You see two ways to approach a problem. You say, this one is really beautiful. That's the one I want to do. This one is not beautiful. That's the one I don't want to do. It turns out, it's an amazing, I think it's just a fact, that 99 times out of 100, the more beautiful one is the one that will work because you've seen a better structure in mathematics. You have to let yourself be guided by taste, beauty, and of course by your personal experience. If you're beginning mathematics, you look at several problems and you say, oh, that one is more interesting. Then 5 years later, you say, no, that was wrong. This one is more interesting. 20 years later, you say, even that one is more interesting that I didn't realize. So it evolves. But the point I want to make with this whole lecture is that even a very experienced mathematician, like me, I'm 70, and as you heard, I started being a mathematician when I was 20, I cannot tell if I see a new problem, if I have a new idea or somebody tells me an idea, is this a good idea, will it work or not? Of course, sometimes I say no, and sometimes I say yes, wonderful idea. But very often you don't know. And so I want to give you several examples, some for you to play with and some historical. And I hope I get through the lecture. I don't know when I started. Does anyone know when I actually started? There was a lot of, what time?
440.
Maybe 440, yeah, because there were a lot of technical problems and introductions. Okay, so let me start with my first example. So I'll probably forget to number the examples. I've numbered them in my notes, so I don't forget, but I forget everything anyway. So the example is I'm going to give you two statements. I will give to you two statements in a moment. I'll write them down. Both are true. So I'm not asking you to solve anything. And relatively elementary to prove. Although one is easy, one is much easier to actually prove. So one, if you ask any mathematician or even any student, he or she will solve it in 2 minutes, and the other one, it might take 2 hours. So they're both elementary, but that's not the point. One connects with many, and when I say many, I once made a list, there were like 10, with many fields of mathematics and of physics. Ranging, I won't make the list because since I'm writing, it would take too long, but I'll say from my own field, my work with Stavros Garifalidis, your colleague, that's three-dimensional hyperbolic geometry. If you don't know what hyperbolic geometry is, just believe that there is such a field and it's very interesting. So that's at one extreme of pure mathematics to the famous, I'm sure most of you, or all of you have heard of it, Schrödinger's equation in quantum mechanics. The other is just a fun exercise. Sorry, is that okay? Soon I'll exchange them. So the other, as far as we know, of course, I may be wrong. Somebody may discover in a year that this one is extremely interesting, but so far it hasn't happened as far as we know. So this is kind of a problem you might put on an Olympiad, a competition for high school students, but it's not a deep mathematical thing. So let me give you the two statements. And what I want to do is to let you vote. So I will write them A and B, and I will say A, and you either raise your hand or say yes, A, and then I'll say B, and we'll see which one gets more votes. We won't have the votes of the people in other universities because we can't hear them shout. This is not too smart. This one covers that one. Somebody designed this who is not a pure mathematician. So, statement A. So I'll say it without any formulas, but then if you are mathematically trained, it's a lot easier in formulas. I'll write it, but if you don't like formulas, just ignore it. Given a sequence of numbers. Now, when I say numbers, there are two main kinds of numbers. There are many kinds, real and complex. But for here, I'll stick to integral, so whole numbers, like 1, 2, 3, or for that matter, -1, 0, or fractional, like, 1/3. So let's just allow those. So that's what's given, and it satisfies. So you have a sequence, and it satisfies the following property. Each number of the sequence, comma, increased by 1, so you take the number and you add 1, is equal, so this symbol I think everyone knows, it's not really a formula, I can write is equal to the product of its two neighbors. And the claim is, the theorem is, statement, this sequence is automatically periodic. It repeats. Period 5. It's really quite remarkable. So let's test it. Can somebody say the first number? Not too big, please. 7, okay? And then the next one. Come on, somebody must know at least one number. 2. Okay. So the next one, I have to increase 2 by 1, that's 3. And 3 must be the product of 7 and the next neighbor. So 3 is 7 times something, then that something must be 3/7. Now I do it again. This one, if I increase by 1, you could have taken easier numbers, is 10 sevenths. 1 plus 3 sevenths is 10 sevenths. 10 sevenths is 2 times 5 sevenths. Now 5 sevenths, if you add 1, is 12 sevenths. But 12 sevenths is 4 times 3 sevenths. So now we get 4. It got more complicated, now it gets simpler. 4 increased by 1 is 5. 5 is 5 sevenths multiplied by 7. And 7 plus 1 is 8, which is 4 times 2. And now I don't have to go on because once I get 7 and 2, it's going to repeat forever. So you see the theorem I told you is true. Indeed, the thing has period 5. Okay, now I come to B.
I'm sorry, sir, but I don't quite follow why, how are you operating about these sequences?
It's written. Each number, for instance, 3 sevenths, increased by 1. So I add, if you are a mathematician or you know notation, let me write, I have a sequence of numbers xn. Each number, if you add 1, is the product of its left neighbor and its right neighbor, xn minus 1 times xn plus 1. So this number plus 1, so 3 sevenths plus 1, which is 10 sevenths, is 2 times 5 sevenths. It's the product of the two neighbors. That's the rule, as written. It's actually not terribly important. It's an example. Okay, now, B, it'll have very similar words. Given a sequence, and I won't write it all out again, of fractions or integers. Here we could even stay with integers. Here you kind of need fractions. Given a sequence that satisfies, and now I have a slightly different property, but it looks very similar. Each number, comma, taken without sign. So if the number is plus 5, you just take 5. But if it's minus sign, minus 5, you just drop the minus and you put 5. It's called the absolute value, as every mathematician, of course, knows. And this one is now, this was the product of its neighbors. This time it's the sum of its neighbors. And this time, the new claim, so I told you I'm going to make 2 statements, both are true. I checked one in an example. Here, this sequence, very similar, is periodic. Period 9. So let's do it. Since I was given these numbers by the audience, I didn't influence. So let's take the same 2 numbers, 7 and 2. So 2 is already positive. So 2 without its sign is 2. 2 must be 7 plus the next number. But 7 is bigger than 2, so the next number has to be minus 5. So that 7 minus 5 is 2. Now 5 without its sign is plus 5. So that's 2 plus 3. You know I didn't prepare this because I didn't know what numbers you would say. 3 is already positive, so without its sign it's 3. 3 is minus 5 plus 8. 8 is positive, so 8 is 3 plus 5. If I make a mistake, please tell me because it's very embarrassing. 5 is 2 plus 3, 3 is 8 is, I'm supposed to be able to do arithmetic, but not in my head while I'm talking. Okay, 5 is 8 plus minus 3. It's a really kind of stupid example. Plus 3, because you take without the sign, is 5 plus minus 2.
So the fourth number should be minus 3.
Which one?
Fourth.
No. 3 plus 2 is 5. Here, I'll write this form, the 2. This was A, and for B, each number, absolute value, so with the sign, is the product of the two neighbors. So here, plus 5, plus, thank you, the sum. So here, plus 5 is 2 plus 3. Plus 3 is 8 minus 5, plus 8 is 3 plus 5. 5 is 8 minus 3, 3 is 5 minus, I think I've done all right. 2 plus 2, because no sign, is minus 3 plus 5. Plus 5 is minus 2 plus 7. 7 is 5 plus 2. Yeah, but now I'm in good shape. Because once it repeats, it will go on forever. 1, 2, 3, 4, 5, 6, 7, 8, 9. So both, anyway, you can believe me, both theorems are true. Whatever numbers you give me, one sequence has period 5, the other is period 9. Now comes the point. Vote. So one of these two is deep, and one is not deep. It's just a cute problem for high school competitions. So which one is deep? Is it A? If you like A, raise your hand. Okay, is it B? Well, a lot of you don't seem to have enough hands because it was much fewer hands than people, even if I add the A's and the B's. But maybe you only raised a little. But I think B was more popular. I think there were more votes. If that's the case, then you're wrong. But there's no way to know. Even professional mathematicians, unless they happen to know these applications, will not be able to guess. In fact, this one is deep. It's not at all deep. In fact, I said one is very easy to prove. A is very easy to prove. B is much harder. But B is not interesting. So let's call it a bad question, since my title is a good question and a bad question. And bad means you can ask the question, it's fun, but it's only fun. It doesn't go anywhere. So far as I know, no mathematics will ever come of this. The other one goes a long way. So now let me give some historical examples, and I'll try to do them in historical order. So then I need my notes, because I'll certainly forget. So I start, 2,500 years ago with, so a problem, this goes back to Theaetetus, I don't know how to pronounce it, which in Latin is Theodorus. So he was a friend and a very good mathematician, a friend of Plato, who wrote up many of his things, and his dates are 470 to 400 BC. So the question is this: if we look in dimension 2 at regular polygons, you have the regular triangle, so an equilateral triangle, all three sides are equal, all three angles are equal. And then you have a regular square, all sides are equal, all angles are equal. And similarly, you have a regular pentagon. I can't draw very well, but that's it. And then you have a regular hexagon, and then you have a regular sevengon, etc. There's a regular polygon with any number of sides, starting with 3. This is kind of obvious. But in dimension 3, where's Zoe? I need the first slide. You're there, but we don't have the screen yet. Maybe I'll be okay with just 2 boards for the moment. So if you put it down, but I think I won't need a slide for a while. So, oh, well, it's okay because it's covering up what you already saw. The problem is this, but it's not happening. No, it doesn't matter, it's fine. But it should be quicker because it's very unimportant. It's a small slide. Maybe I should have said it earlier. I thought the screen would be already in front. Can you already show the picture? That would be good. Let me save time. Yeah, so I think all of you have seen this picture in your life. Tetrahedron, cube, octahedron, icosahedron, dodecahedron. These are the 5 regular polytopes in dimension 3 that were discovered by Theodorus or Theaetetus 2,500 years ago. I don't know the history if he already had an argument that this is the complete list, but we've certainly known that for a very long time. This is a good problem. It leads to big developments. For instance, group theory came from this kind of thing. There are groups behind each of these. A lot of modern geometry, well, specialized things like Hoxler geometry, representation theory. This picture influenced a lot of algebraic geometry, the icosahedron and so on. So this turned out to be a very good question. But if you just heard it, especially 2,500 years ago, in 2 dimensions, we have a triangle, a square, a pentagon. What happens in 3? Well, I found these, they're very pretty. We can use them for art. You wouldn't think that this is so important. But this was a very good question and led to huge developments. So I think I won't need a slide for a while, but maybe I can use the right board, so we leave the screen. But I don't need a slide for a bit. Okay, so I'll try to go on. This is very confusing. I'm not a technological person, so I think we can relax. So this is, that was an example from 2,500 years ago. My next example is one of my favorite mathematicians, Pierre de Fermat. So French, he wasn't a mathematician, he was a lawyer or a judge, but he was a pretty good mathematician for an amateur. So he, and maybe Diophantus, who's my other favorite mathematician of number theory, who was much, much earlier, like 1,400 years earlier, so roughly plus 150 of our era. But it's not, no, we don't know if Diophantus knew that, but there's very strong evidence that he knew the thing I'm going to say. And he asked a question which sounds like a bad question, but turns out to be a very good question. But I'm going to contrast it in a minute with several other questions, and they all sound, if you haven't looked at them, about the same. Some are good and some are bad. And I claim nobody knows. You need a lot of time studying them. So he asked the following question, which may seem very silly. If P is a prime number, so we have two classes. I think everyone knows this, but I'll remind you, prime numbers are numbers that cannot be factored into smaller numbers. So 1 cannot be factored, but it doesn't count. So there are 2, 3, 5, 7, 11, 13, 17, 19, etc. And then we have the squares, I think that everyone knows. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 16, 25, 36, and so on. So we have two famous sequences of numbers, the primes and the squares. And he asked, which primes are sums of two squares? And actually, we know that Diophantus had asked that question, and we have every reason to think he knew the answer, surely without a proof. But we don't have documentary evidence. So let me do an experiment. I'll just do a few of the numbers. I can take a table so I don't forget, but I think I know them by heart. No, that's really silly. I know the primes. So let me take all the primes up to 50. Otherwise, you don't have enough. This board is too small. I think I better take this one. Let me take 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. So I just took all the primes up to 50. I hope I didn't forget any. And now we ask, is it a sum of two primes? I'll write that in red. Oh, well, if they're going to play music, I can write at the same time. So this is 1 plus 1, but it's not interesting because they're equal. This is not. 1 plus 4, not. 4 plus 9. 1 plus 16, not. 4 plus 25, not. 1 plus 36, 16 plus 25, not. So far, all I've discovered for you is that every prime either is the sum of two squares or it's not the sum of two squares. That's not very interesting. But Fermat and Diophantus asked, can we tell which ones? And so let me do the following. If I have my prime, well, except for 2, which doesn't count, they're even and they're odd. I mean, they're equal and they're both odd. Here, they're distinct and one is even, one is odd. So this is an exception. But in any other case, if P is a prime, now I do write a formula, you can take half of P, but you can't take quite half of P because it's odd. You subtract 1 and then you take half. So let me now write under the primes, the number, I take the prime, I subtract 1, so 2, and I divide by 2. So it's 1, 2, 3, 5, 6, 8, 9, 11, 14, 15, 18, 20, 21, and 23. And now I'm going to circle the ones that worked. So the ones that were two squares, I'll take yet another color, why not? All these colors. So 5 worked, so that's a good one. This failed, worked, failed, worked, failed, worked, failed. Who sees the pattern? I mean, not people who know, of course. They're all even and they're exactly the even. So the answer that Fermat found is if P divided by 1 over 2 is an odd number, it can never work. That's very easy. But if it's an even number, it always works. That's not so easy. Actually, there are about 600 proofs known of that second theorem. And the shortest one in the whole world is due to me. It's a one-sentence proof, but it's very artificial. It's a stupid proof, but it's short, like me. Okay, so that's Fermat's not his last theorem, his correct theorem. Okay, so let me write again this question. So you have a prime P, and you can ask, is it x squared plus y squared? But here, I was automatically assuming x and y were integers. I mean, nobody complained, but when I wrote 1 plus 4, 4 plus 9, they were always whole numbers. What if I looked at fractions? Well, there are many more squares of fractions, but it turns out that, so the answer is nice. So it's true, that's Fermat, if and only if P has the form, well, I'll just put P minus 1 over 2 is even. Okay? But now you can change the question, and in mathematics, you always, if you have a good question, you try many variations. Some will be fruitful, some will not. So now we still ask this, but now we allow X and Y rational. Same question. Well, the answer turns out to be the same answer. So if P minus 1 over 2 is even, it's already a sum of two integer squares. That's certainly fractions, but if it's not, it still doesn't work. That's actually very easy. But now, let's go on, and let's try P equals x cubed plus y cubed. So I add x times x times x instead of x times x, plus y times y times y. For instance, 1 plus 8. Well, that's not a prime, but I'm sure I can I think of a prime that works? I didn't prepare a good prime, but anyway, you can certainly find a prime that has this form with two integers. So with x and y integers, so whole. Or you can ask the same thing. So we ask, is this possible? Or we can ask, is it possible with fractions? Now I'll just tell you the result of 200 years of mathematical research. So this is a good question because it has a wonderful answer. This is a good question. It has an equally wonderful answer. It's in fact the same answer. This is a bad question, and this is a good question. And if I continue, we can ask, how about P? Is it a sum of 2/4 powers, both integral? Or we can, I already had a question mark. Or is it a sum of 2/4 powers if I allow rational numbers, fractional? Well, again, as far as we know, but I think here we really do know, these are both bad. So I want to explain what I mean by bad mathematical problem. I don't mean that the person who asked that problem is stupid or has bad taste, or it's a moral thing, he's a bad person. It's simply that problem doesn't lead anywhere. It's a dead end. We have thought about it for a long time. It's often the most interesting problems that are bad. We know they're bad because we've really thought about them. They sound nice, but nobody can do anything if there's no structure. So people make huge computer programs. The answer here looks completely random. But here it wasn't random. You saw, you all found the answer if P minus 1 over 2 is even. Here it's much more complicated. So this problem with fractional numbers, I can tell you the history in 2 words. Sylvester, a famous English mathematician, asked this question and proved several results in the 19th century. And my colleague, well, he wasn't yet my colleague, Fernando Villegas, and myself gave an almost complete answer in, I think, 1995. So this problem, what's good about it is not that we could write a paper, that was good for us, but that somebody could write a paper, there is an answer. You can do something, and this is the problem that Professor Zhang mentioned, the BSD problem. You get $1 million, and I will explain also very informally in a week in a seminar talk, which will also be Zoomed, so people from other universities, as far as I've understood, can listen. I'll try to explain very simply what that conjecture says, and then you can all earn $1 million. But I promise you, it's not easy. Okay, so let me go on. So that's 2 examples of problems that I think no mathematician beforehand would have known that this problem is not solvable. Now this is called the theory of elliptic curves. This is called integral points in elliptic curves. One is a dead end. You cannot prove anything. Well, you can prove there are only, for a given prime, there are only finitely many solutions, but in fact, that's trivial here. Whereas the other has structure. And if you put 4th powers, there seems to be absolutely nothing. It's completely random. So it's not a good math. A good problem is one that leads you further. So now I need the next slide. So the famous 7 bridges. Yeah, so this is a slide of a translation of a page of Euler. Euler you've all heard of, 1707 to 1783. And here he explains that there was a problem that, I'll make it bigger in a second. Everybody was talking about this problem, and he's very proud. He said, I solved not only this problem, but a whole class of problems of the same sort. So if you go to the next slide, we can see, you can't read this anyway, but he said, I was able to determine always whether it works. So this was the problem. In the city where people discussed this, Königsberg, there was a river, and in the middle of the river, there were 2 islands and bridges, the way you see. So there were 7 bridges, 1, 2, 3, 4, 5, 6, 7. And the question that people asked as a puzzle was, if a person starts in one place, can he make some path, any path, and cross every bridge exactly once and come back to the original place without crossing any bridge twice. You can go in either direction. And Euler wrote, people discussed this, and some people thought it could be done, some people were sure it couldn't, but nobody could make a path, and nobody could prove there wasn't one. Euler proved it cannot be done, and he said he solved a whole class of similar problems. This is a completely silly problem. This is a problem people asked each other over a glass of wine in the bar. It's just a fun problem. But the solution, this started several fields of mathematics, graph theory, combinatorics, optimization. This turned out to be very fruitful. And of course, Euler, being a great mathematician, went much further than just solving the one problem he set up. And this is the modern theory of graphs, that there are certainly specialists in every university, maybe in the world, in every math department. So I think I won't need any slides for a while. So maybe we can move it up, and I can use more boards. If you can do that. So this eraser works beautifully. If we had erasers like that in Germany, we wouldn't have to use all that water. Okay, so my next problem is a little later than Fermat. It's Euler. Well, this was already Euler, so it's again Euler, second Euler. So my story starts earlier, in 1644. A man that I'd otherwise never heard of, with an Italian name, but in Basel, asked a question, and so he was in Basel, and this became known as the Basel question, or the Basel problem. And it was solved, I have to get the dates wrong, in 1734. Euler, who was then a young man, and also lived in Basel. Now we have to wait for the music, but it's not very long. So the question was this. Remember, we had the squares before. So since you can't hear me anyway, I'll quickly write them. So we had already the sequence of squares. So 4 times 4 is 16. And so what people already knew is if you take their reciprocals, 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, this is an infinite sum, but some infinite sums have the limit infinity, but some converge to a limit. Of course, every undergraduate in mathematics learns many examples. This is an easy exercise in one line to show that this one converges. So this is some number. Let's call it S for sum. So this is an infinite sum. And the question is, the Basel problem of 1644 is, what is S? So people knew it converged, but they had very bad numerical methods. And so they knew it was approximately 1.64. But many numbers are approximately 1.64. That doesn't tell you anything. Then came Euler. Euler was a genius. And in this case, in my view, he was a triple genius. He solved this in 4 steps, and each one of which shows a mathematician of the highest rank. So Euler, first, found a theoretical way to calculate this number. So the series converges extremely slowly. If you take 1,000 terms, which is impossible by hand, and of course it had to be by hand at that time, it would never, you would get 2 digits. I mean, it's very, very slow, and you would make mistakes. To calculate S to high precision. This was a brilliant piece of mathematics and is now a famous formula and is used by mathematicians more or less every day. Secondly, he actually did it. He calculated S. That's also not obvious. By hand, of course. It's a lot of work, and you shouldn't make any mistakes. And he did the work, and he didn't make any mistakes. To my embarrassment, I didn't learn it by heart, so I'll have to copy it out. That's Euler by hand. Can you imagine finding that by hand? I mean, this shows you what it means to do research with no tools. You know, no internet, no computer, no nothing, just your head. Okay, then I think this is the biggest step. He recognized this number. So excluding people who know the answer, who recognized that number? Who can say, oh, 1.644931, that's, but Euler could do that. He recognized this number. Exactly. S is pi, the famous 3.14 squared divided by 6, exactly, at least to 20 digits. So he was pretty convinced. And then about 10 years later, he finally proved it. It's not at all, I mean, even today, it's not obvious, but he had to invent calculus, logarithms, he had to invent everything we use today. But to me, the most startling is this, that he looked at this number and said, oh yeah, sure, pi squared over 6. Okay, so this is a good problem. Now, why do I say it's a good problem? Well, one reason is because Euler solved it, which was very nice for Euler. He immediately became famous all over Europe, got a professorship, not a professorship, became an academician in St. Petersburg and lived most of his life in Russia, never really learned much Russian. But so it was a good problem for him, but it's a good problem because it has an answer. People had no idea this number S could have just been a random thing, no answer. And in fact, Euler asked more questions. Let's look at S3, just like before, I'll take the cubes. So 2 cubed is 2 times 2 times 2, that's 8. 3 cubed is 3 times 3 times 3, that's 27. Then 4 times 4 times 4 is 64. Well, you can compute this, and Euler did, to the same number of digits. Okay, but there is no answer. Euler wrote, he said, I tried very hard to recognize this number. I failed. It seems to be nothing in terms of other numbers. And today we still have failed. As far as we know, this number cannot be expressed in closed form. Therefore, it's a bad problem, but it wasn't originally bad. It's a perfectly reasonable problem, just you can't do anything with it, of recognizing this number. But then Euler went on in a paper 15 years later, in 1749, he said, let's look at the fourth powers. This one turned out to be pi to the fourth divided by 90. So that was a good problem. And then the fifth powers was bad and the sixth was good. All the even powers were good and all the odd powers were bad. But he didn't know that before he started. But he spent several years studying it. And then he knew. That's the point I'm making. Nobody is so smart, even if they're Euler, that they know which problems will work out. But that's somehow what research is about. So here we see examples of good and bad problems. So I have one fun one that I want to tell. I still have time, right? You said 40? Oh, good. Then I actually will be able to finish what I prepared. That's almost unique. So I'm going to quickly give you 3 examples. This was now, we got up to the 18th century. I'll tell you 3 from the 19th century and then one I like a lot from the 20th century, actually from the 21st. It was only 5 years ago. It was shown to me by somebody who was on that picture on the screen a bit ago. So let me give a question that's a bad question. So I'm not going to go, I have 3, I'm not going to go into detail at the second because it will, well, it's kind of fun. I'll do it very briefly. So here's a bad problem. Certainly in the 19th century, people already were very interested in which numbers are algebraic, transcendental, rational, this and that, and their decimal expansion. We know that if a number has decimals which repeat, like 0.142857142857, it's rational. And so you can ask, and there's certainly many mathematicians have asked this question. So we take the number pi, it's maybe the most famous constant and the most important in all of mathematics. So when I was a child, I learned several digits, I think 20, and I never learned any more, but I still remember the ones I learned as a child. Just out of curiosity, that's 20, I think. Who here knows more digits of pi than that? Raise your hand. Does anyone? Yeah? How many?
I don't know, but it's...
But you once knew more. Well, because I have a nice story. The same mathematician, my friend whom I mentioned, Henrik Lenstra, one of the LLL that they use in GPS, he's a wonderful lecturer. He once gave a popular lecture like this for non-mathematicians, or well, mixed. And at the end, somebody said to him, Professor Lenstra, how many digits of pi do you know? That's not what mathematicians do. But he looked at him and he said, I know them all. And the person looked at him, you know them all? Of course, he said, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is true. But the question, are the digits, well, we have 10 fingers, so they're decimal digits. Of pi, equidistributed. In other words, if I take the first million zeros, and they have many more digits, I think they've calculated 100 billion or some huge numbers, 10 to the 11. What's the word? Something distributed. Uniformly distributed. I'll just put uniform. In other words, if I take the first million digits, I should find 100,000 ones, 100,000 twos, and so on. Of course, if you do it on the computer, that's what you find, no surprise. That's what would happen if it were random. If it were different from that, that would have to be a mathematical theorem with a proof. Because if it were different, if half of the digits of pi were 7s and the other half were always 4s, there would have to be a reason for that, because that's not random behavior. But if the computer tells you it's completely evenly distributed, you can try all of your life to prove that. Almost certainly, not only you cannot do it, nobody can ever do it, because probably that's not a theorem. It's not a mathematical theorem. It's simply true for statistical reasons. But a theorem has to possess a proof, a finite list of statements which will prove it. And there probably is no theorem, because they're probably essentially random. So this is, to me, a quintessential example of a perfectly good and interesting question. It's not uninteresting. We would all love to know. It's a very natural question. That doesn't mean unnatural, but it doesn't lead to any research. You cannot do anything with that. So that's a bad problem. Then another one, so that's one example. I want to give 3 and then the final one. So the second is the 4-color problem. Now I do need a slide. Zoe, where have you gone? Ah, there. Maybe show a slide somewhere. So in 1862, I think, I've it written down, it was conjectured, I won't say the names, De Morgan and Guthrie, and in 1976 it was proved, I again won't say them, I'll say the names not right, Appel and Haken. So this problem says, here's a map of the world, and it's been colored with exactly 4 colors. And the thing that was discovered empirically is any map, no matter how complicated, you can color all of the countries using only 4 colors so that no 2 adjacent countries have a common border with some minor technical thing. Now, that was proved a few years later with 5 colors. That's quite easy. 4 colors took more than 100 years. So this problem, in my view, is a good problem and a bad problem. It led to a lot of research, but the final proof, there are now several improvements of this, but they're still all with a huge use of computers. This proof cannot be done by human beings yet. It can only be done by human beings thinking and analyzing together with massive computer calculations that might have come out differently, and then it would be false. We have no understanding of why it's true. So it is good in that it led to interesting research. It also led to a lot of developments in computer science, but it's not really a good mathematical problem. It did not lead to a clearer way of seeing, let's say, graph theory. And then my last example is, I think around 1870, I don't remember the year, Mertens asked a funny question. So if I have a number, let's say 105, every number, it was proved by Euclid, every number is a product of primes. So for instance, 105 is 3 times 5 times 7. Here there are 3 primes, so let's call this an odd number. I mean, it's not an odd number, let's just call it odd. Well, I'll put an O for odd. But if I take, for instance, what's another number? 11 times 7. So 77 is 7 times 11. That is only 2 prime factors, and that's an even number. So let's say even number of prime factors. And finally, if I take, for instance, 76, which is 2 squared, so 2 times 2 times 19, then we don't really know, should I count the 2 twice or once, so we just cross it off. So Mertens said, let's look at every number. And if it has repeated prime factors, we just forget it. But if it doesn't, we count it as odd, if it's odd, and even if it's even. And the question he asked, so Mertens, are the odds and the evens equally distributed? Randomly distributed, as if it were just flipping a coin. So quickly this morning, I can show you the numbers because it's very short. I computed a few values, which now I can't find. Yeah, here. So I took the numbers from 1001 to 1010. Okay, and I factored them on the computer, so 7 times 11 times 13. If you're taking notes, don't bother. It's completely uninteresting. I'm just giving you some numerical data. This one, 1003, is 17 times 59. My computer did this, so it would take me a long time. 2 squared times 251, so we cross it off. 5 is 3 times 5 times 67. The next is 2 times 503. The next is 19 times 53. The next is 2 to the 4th times 3 squared times 7. So it has repeats. We cross it off. The next is a prime. And the next is 2 times 5 times 101. So if I count, this is 3 primes, so it's odd. 3 primes, it's odd. 2 primes, so it's even. 3 primes, so it's odd. 2, so it's even. 2, so it's even. 1, so it's odd. 3, so it's odd. So here it's 3 to 5, 5 odds and 3 evens. But I quickly asked my computer to go up to 10,000. So some of the numbers were not odd or even, but there were 3,053 odds and 3,030 evens. So that is randomly distributed. That's what you'd expect if you flip a coin. Not exactly the same number, but very close. The difference should be of the order of square root of n. And so Mertens asked are these numbers statistically distributed. So it's been known for a long time, Mertens certainly knew, that half of them are even and half are odd. So it's roughly 50%. But we want to know that it's as close as this, like the square root of 10,000 is the difference. That, so the answer, yes, which we don't know, it's still open, is equivalent to the Riemann hypothesis, which is also one of the $1 million Clay problems and the most famous open problem in mathematics. It's simply equivalent, it's a 2-line proof. So that's a very good problem and a very deep problem. So now in the last 5 minutes, I might go a minute over time, but if you don't like it, I'll just walk out. Because I have to tell you this problem because it's Chinese. So now I need the first slide. So I was sitting with Di Yang, whom you saw on the USTC board, in a restaurant in Bonn, and he said he had his phone, like every Chinese person, and he said, oh, there's a brand new problem on the Chinese internet. It's such a nice problem. So can you see it? Is it there? Maybe we need it on both sides. Can you do that? Because it's a little too small. I could try to say it. No, I'm not going to try. I'll translate it into English in case your Chinese is not good, not very likely. It says the nastiest problem in the history of mathematics. That's more or less true. The next sentence is completely stupid. It says 95% of human beings who try to solve it can't. I made an estimate. I got 99.999998. My estimate is that there are 200 people in the entire world who could solve it. I'm one of them, but you have to first be a professional number theorist, B, be a specialist in elliptic curves, C, love to compute, and use Paris. And I think there are probably only 200 people in the world to satisfy. You don't have to be a genius. You have to know the theory and use the computer. But it's not 95%, I assure you. And let me tell you why it's not 95%. Please show us the next slide. This is the smallest solution. The answer is yes. So you see, this is not something you will see in your head. Definitely not, even in my head. And I used to be good with arithmetic. Now I lost the eraser. Do you know where it is? Ah, here. Yes. So let me first write the problem in case you can't see it. So it's more or less the first formula I wrote. If you're a non-mathematician, I really hate formulas. Just say we have 3 numbers, A, B, and C, are positive. Well, it's written there. Sheng, sheng, fu. So they're positive integers. So can you find that there exist? Are there? Yo, mayo. Are there? A, B, C, such that you take one of them, A, and you divide by the sum of the other 2. Then you take another one, B, and you divide by the sum of the other 2. And then you take the third one, you divide by the sum of the other 2. And then it's required by the problem there should be 4. Now you will surely say, even if you're a mathematician, and certainly a non-mathematician, that's completely idiotic. You would have to be mad to care about this problem. Who cares if there are 3 numbers? It's completely artificial, and it is. But it's very carefully constructed to be interesting. It's actually a good problem that sounds uninteresting. The digits of pi was a terrible problem that sounded very interesting, but it doesn't go anywhere. This problem leads you deep into the theory of elliptic curves, which I'll talk about for non-specialists on Thursday. And I can prove to you, even if you don't know what an elliptic curve is, that it is deep, that it's a good question. Actually, you know that. Who can tell me the proof? It's on that screen. If this were not a good mathematical question, there would be no structure. Then we could not possibly, the human race could never have found these 3 numbers. These 3 numbers have 80 digits each. Well, one is 78, 79, and 81. These are 80-digit numbers. If you try by brute force on a computer, that's 10 to the 240. Let's say the computer does 10 to the 10 operations per second. No computer can do that. There are 10 to the 7 seconds in a year. That's 10 to the 18. There are 10 to the 13 years in the history of the universe. Now we're up to 10 to the 27. This is 10 to the 240. You cannot just solve this. People think, well, computers can do anything, as we saw this morning with the, anyway, they can't. So the point is that this is not solved by computer. This is solved using the brain only. Of course, at the last stage, to actually get the numbers, you do the arithmetic by computer. Naturally, none of us are crazy enough to multiply out 100-digit numbers. But the fact that this is known, that anybody knows this solution, I mean, it was on the internet, I found it, and many people found it, but as I say, probably not, definitely not 5% of the world's population. The fact that you can do it at all means that there's a deep theory that you can use if you understand how the theory works, and that there's some structure. So I'll just end very, very briefly. Like all my other problems, we can vary this problem. I want to get the numbers right. So I'll take my sheet. So here, so we have this. Let's change this number. So if I put 4, then these numbers have 81 digits. And you might think, well, the person who invented this problem carefully made the problem to make a huge thing to impress everybody. But actually, I tried many other numbers, and so there's a paper on this much better than what I did. We've tried lots and lots of other numbers. The number of digits is actually always much bigger. This is the smallest that's ever been found. So I'll give you 2 more examples. If you replace the 4 by 178, then the number of digits that's 400 million digits. If you write that out, if you printed it, that would be 3 20-volume Oxford English dictionaries, unabridged. And then if you take 896, nobody knows the exact numbers, but we know that it's more than 2 trillion digits. That would fill up an entire library if you could print it out. And we don't know the number, and we couldn't print it out if we did, but we know it has 4 million digits. This in itself tells you it's a good problem, because there must be a lot of theory in order to be able to say such things. And finally, I'll end with one purely mathematical statement, which I failed to prove, and I'm a professional number theorist. I thought that's impossible to prove. If you put any odd number here at all, 5, 7, 9, then there's never any solution. And I didn't even believe that when I saw that. I thought, nobody can prove that. But it has been proved, Bremner and MacLeod about 10 years ago, 7 years ago. So I finished with those examples from the Chinese internet.
So, a wonderful lecture by Professor Don Zagier. Any questions for Professor Zagier? Yeah.
You have raised many examples of the problems with some of them are bad. But can you briefly summarize by what standard?
No, I can hear you. It's a good question. I'm a little disappointed because I thought I spent a whole hour explaining the standards, but it's not very well defined. It's not like passing a test. You passed, you failed. It's my test. It's very personal. But my criterion was if a problem can lead to deeper insights to develop a new theory, you start with the problem. Everyone understands the problem. There's no trouble understanding the question, are the digits of pi equidistributed? You don't have to know anything. Now you studied for 10 years. And now you know exactly as much as your grandmother. If she's still alive, you still know that you don't know anything. The digits of pi, it's not good because it doesn't go anywhere. It is no, as far as we know, there's no structure. There's no mathematical structure behind it that we can analyze. There's nothing to do. If you're a mathematician, you want to roll up your sleeves and do work and start. But there's nothing to start on. As far as we see, there's nothing. If you take the example, like this problem, which is a typical, well, not typical, it's a particularly nasty problem, as they said, from the theory of elliptic curves. The theory of elliptic curves, I'll speak about the week, has a very rich structure. It's not obvious. It takes a long time to see why it's there, but we now know it's there. And therefore, you can take a problem and you can study it and do things. So, for instance, Di Yang showed me this we were having dinner in a Chinese restaurant. Dim Sum, and he said, okay, John, it says 5%. You're short in the top 5% of the world for number theory. Can you do this? So it was a challenge, and I did it just barely within 2 hours. So I said, I think I could do it in 2 hours, but I used a big computer. So, but the point is, I knew the theory. I know elliptic curves. I've taught many courses on them. I've written many papers. And so I knew what to do. The theory guides you. But that theory came into existence because of problems like this. Actually, this problem is an artificial new one. It was posed only 7 years ago. But the problem that I mentioned before, it's somewhere on the board, but I can't find it. So I'll go back to the problem of Sylvester. And that I will talk about on Thursday. Which primes are sums of two cubes? Then first you think, well, it's just like which prime is the sum of 2/4 powers or squares. They all sound the same, but squares turns out very elementary. 4th powers is hopeless, and cubes with integers is hopeless. But this one you can develop a theory, and the theory is huge. There may be 50 books on elliptic curves, thousands of papers. It's a very deep theory that comes out of asking this type of question. So you cannot tell at the beginning, if you're, say, a student, and you look at two problems and you say, which is beautiful, which is good and which is bad in the sense that I said. You cannot tell. That was the point of my vote at the beginning. The people who voted B were not stupider than the people who voted A. There's no way to tell. They were guessing. But if you work with them a while, then you will see one stops. You can develop and then it doesn't go anywhere. The other one leads you to the next thing and the next thing and the next thing. So to me, what I meant by good is good from the point of view of the progress of mathematical research. It's one that will lead you to new ideas and new structures. All of mathematics is about structure. It's certainly not about numbers, shapes, or any algebras, any specific thing. It's structures, but there are many different sorts. And when you first look at a thing, it has no structure. It's just a bunch of things. But the more you look, of course, the more you see. And so to me, a good problem is one that helps you to find the deeper structures.
My confusion was I thought we should be able to see what's the question or that question.
Absolutely. No, that's what I said at the beginning when I had you vote. It was not to embarrass the people who voted the wrong way. It was to show nobody can know. I showed you two simple statements, A and B, very artificial. The two sequences, period 5 and period 9. Which is deep? It turns out the deep one, but it's very easy, is the period 5, which is quite hard to prove. By the way, it's a good exercise for any of you who are undergraduates or professionals, for that matter, in mathematics. Try to prove, not the one with the 5, you'll do that in 1 minute. Even if you try not to prove, you cannot fail. But try to prove the one where the absolute value of x is the sum of its neighbors, period 9. It's hard. But I mean, it's elementary, but it takes a few minutes. But that problem leads nowhere. And the other, and nobody, I claim no mathematician, if he hasn't seen them, can tell. So what I wanted to say is, if you're a young mathematician, be flexible. Don't look at a problem at the beginning and say, oh, that's a dull problem. I don't want to think about it. If you say, I don't like that field, that's your taste. But you cannot tell if the problem is good until you try. A very good question, thanks. So, is somebody else asking a question?
I have a question.
Yeah.
So first time before I ask my question, I would say thanks to excellent speech delivery. But I have to point out that it seems that on the map you present to us, Taiwan province and then China is not in the same color. So
I didn't understand. It seems that what?
on the map you present to us, Taiwan province and then China are not in the same color. So frankly, I am disappointed about that.
Oh. I didn't make that map. I found it on a very old thing on some website. Okay, I'm very sorry. Anyway, it doesn't matter in the case of Taiwan because it's an island. You can color it any way you want. It won't. Okay.
So I'm asking this question on behalf of those students who are not majored in mathematics. I am from microelectronics. So how much fundamental mathematics tools do we need to learn? Also, basically, is it the more you learn mathematics, the better? Or after you've reached an amount, a level, the benefits starts to diminish?
To be honest, I'm the wrong person to ask because I've not studied microelectronics. I've studied mathematics. I know a lot of mathematics. I started when I was 6 and I'm still learning and I want to learn more every day. So to me, I learn mathematics because I love mathematics. And so I don't want to know what will I need. But if you are in another field, then certainly the answer is you do not have to know a great deal of mathematics and you do not need any of these criteria, beauty, aesthetics. You want to know maybe what is useful, with what tools can you solve problems in your field. That's completely reasonable, and I'm not saying there's nothing wrong with it. I was talking from the point of view of a pure mathematician who wants to research in mathematics. If you want to do good research, you should be guided, not by thinking, if I solve that, I can do that. You should be guided by this problem looks elegant, beautiful, It's simple. I think I've seen something that other people haven't seen, a U structure. You should follow your nose and your taste and your experience. But if you're not a mathematician, you don't want to find new mathematical problems. You want to understand the mathematics you need for your life. Then I assume you should ask other people in that field, whatever the field is, microelectronics or biology. In your experience, you've been working for 25 years. Which mathematics that you learned in university was useful and which was not useful? And if they say, you know, frankly, statistics was very boring and I've never used it, maybe you skip statistics. I'm saying a random example, but you have to ask people from their experience. But I was talking from the point of view of internal in mathematics, what will lead you further? And so my unique, like your question, my unique criterion is what will lead you to see a little further in mathematics. But of course, if you're not a mathematician, that's not your object. So I can't really answer the question. But thank you very much. And thank you for the comment. I will send a letter to the person who wrote that probably 40 years ago and have him remove it from the internet. I won't, of course.
We allow one more question.
I will ask a more specific one that I have write down a series of integrals, and I want to check whether they are good questions.
Oh, it sounds to me, however, that maybe you should do that privately because the people in the audience may not know what an integral is.
I just want to have you look at it. And
Oh, you just want me to look? Oh, okay. Oh, I can write too. Okay. So it's the integral. If you don't know what an integral is, just shut your eyes. It won't take very long. And then you put a 1, and then it goes up to 6.
Yes. I'm actually a freshman this year, and I just learned all those 6 integrals on the calculator. But my question is, I just calculated all those 6 integrals just with my techniques to do some algebraic operation. So my question is, I think that those 6 calculations don't lead to deeper understanding.
Of course they do. Of course they do. No, I don't agree.
They are all bad questions.
Wait. If you went to 6 and you stopped, of course it won't. But if you went to 6 and you said, no, I see, it was always the same. And then you ask dx over x to the n plus 1, that's much harder. But if you can solve that, then you've made a big jump in your understanding of mathematics. And it can be solved. It's a beautiful answer. And there are 2 different approaches to solve. One is pure algebra, or number theory, basic number theory. And the other is complex analysis, which you certainly haven't yet had. But maybe if you wait 2 years, Professor Irmer will teach you. So you will learn Cauchy's theorem. With Cauchy's theorem, all of these become completely easy. Well, except the first one, which, sorry. When I said the integral, I mean the integral from over the whole real line. If you mean the indefinite integral, that's much harder. In fact, I don't know the answer. Well, I do know the answer, but I don't want to say. It is a good question because if you think about it, you will be forced to discover a big part of integral calculus. However, since Euler discovered all of it in the 18th century, it's more efficient to read it in a book and discover something new. I mean, it's not so exciting anymore. But it is, in principle, it's a very good question. Yeah, and thank you.
You have the honor to present the certificate.
Oh.
Thank you very, very much.
Wow.
For your nice talk.
Wow. Thank you. This is a certificate that I survived this lecture. Thank you very much. Oh, we have to have pictures. Except I don't want to infect you.
Okay, thank you very much.
Yeah, we should use right hands. That's wonderful.
So we have another item.
I've already been warned, yeah. Book signing.
Yeah, the book
I was warned, yeah. Oh, this is really very, very nice.
Recording stopped.